Okay, today, good morning to all of you. Um, my name is Dr. Vinamacharya. Today, I'm going to discuss with you the next module, that is band theory of solids. Uh, this band theory of solids includes the free electron theory of metals, and we need to discuss how many types of solids are there in this. What is the classification of materials? And we need to discuss the density of energy states and the energy band diagram. Next, large theorem for a particle in periodic potential, according to the model in quality to next K diagram, another origin of energy bands in solids, effective mass of an electron. Finally, the distinction between metals, semiconductors, and insulators. Today, we most probably we need to concentrate on up to Lord's theorem. If time permits, we will go for chronic penny model. Okay. Now, what is band theory of solids? This band theory of solids, basically it is a free electron theory of metals. Now, this free electron theory of metals divided into three. There is classical free electron theory that was proposed by Drude and Lorentz. And the quantum free electron theory, there is some drawbacks or some failures are there in classical free electron theory. Those failures are rectified by quantum free electron theory. This was proposed by Sommer failed. Next, and also in those two classical and the quantum free electron theory, some drawbacks or some failures are there that are explained by band theory of solids by this was proposed by Bloch. Okay, now we'll go for free electron theory of metals. Whenever if we are considering the uh, shells or if we are considering the sodium, in that sodium, what about the atomic number? It is going to be 11. Now, how the electrons are moving, how the free electrons are moving within the material. That means the sodium is having in outermost shell only this one electron. That one electron which is moving in between the ions. This obeys the classical free electron theory obeys the classical mechanics, and electron revolves around the nucleus. To obey the electron theory of metals, uh, the valence electrons of the atoms are free to move about whole volume of the metals, like the molecules of a gas in a container. That means whenever if you are considering the gas in a container, how the molecules are moving in a container, just like that, the free electrons are moving. The valency electrons are that are all over free electrons. The free electrons are moving in a solid, just like none. Okay, the free electrons obeys the laws of classical kinetic theory of gases. What are the classical free electron theory obeys the classical kinetic theory of gases? Now, these free electrons move in random directions and collide with either positive ion fixed to the lattice or our electrons. All the collisions are elastic. That means there is no loss of energy. That is, here the electrons are moving. Here the electrons are moving randomly. That means in between if that electrons are collide with the positive ions which are fixed with the lattice or that are bombarded with another electron. That means if you are seeing this one, this is that will collide with another electron. That's why these all the collisions are elastic. That means elastic collision means that means there is no energy loss between the collision. If you are considering the just elastic collision means kinetic and momentum and kinetic energy, the conservation of momentum and the conservation of kinetic energy. That is, uh, momentum before the collision and momentum after the collision is same. And similarly, the kinetic energy is also before the collision and after the collision is same. Okay, that is the elastic collision. Here, the random collisions or the collisions takes place between the electrons or between the electron and the lattice ions is elastic. Okay, now the electron velocities in metal obey the classical Maxwell-Boltzmann distribution of velocities. Maxwell-Boltzmann statistics. This Maxwell-Boltzmann statistics explains the macroscopic particle behavior. That means whenever we are considering the macroscopic particles, for that macroscopic particles is MD statistics obeys that. Okay, now the free electrons moves in a completely uniform potential field due to ions fixed in the lattice. That is, the free electrons moves in a completely unfair, uniform potential field. That means this is a uniform potential field. This total is it is uniform potential field. In this uniform potential field, which is fixed in the lattice. Okay. Now, when an electric field is applied to the metal, the free electrons are accelerated in opposite to the direction of applied field. That means when we apply the electric field to the metal, the free electrons are accelerated in the opposite direction of the applied field. If the electric field is applied in positive x direction, the free electrons are accelerated towards the negative x direction. That means which are opposite to the direction of the applied field. The applied field is in this direction, and the electrons are accelerated towards the opposite to the electric field. Okay. Now, coming to the what are the success of classical free electron theory? It verifies the Ohm's law. That means you know the Ohm's law, that is V equals to V is directly proportional to R. V is directly proportional to R. And generally, we need to represent a condition called at constant temperature. That means without varying the temperature, that V is directly proportional to R. That means there is a linear relationship between voltage and current. Otherwise, there is a change. Okay. At constant temperature, the voltage is directly proportional to the current. So V equals to IR. It explains the electrical and thermal conductivities of metals. It explains this classical free electron theory explains the electrical and thermal conductivities of metals. Next, it derives the Weidmann formula. The Weidmann formula means the relation between electrical conductivity and thermal conductivity. That is, this is called as the Weidmann-Franz ratio. That is K by sigma E. Weidmann-Franz ratio, the electrical and thermal conductivity. That is K by sigma E. K by sigma E is constant. It explains the optical properties of the metals. Now, coming to the drawbacks. What are the drawbacks of classical free electron theory? That is, instead of success seen above, classical theory has some following drawbacks. The phenomena such as photoelectric effect, Compton effect, and black body radiation could not be explained by classical free electron theory. That means this, even though this theory having some success, that is, it verifies the Ohm's law and it verifies the Weidmann-Franz ratio, but it is having some drawbacks or some inabilities that are called as photoelectric effect, Compton effect, and black body radiation. That means this theory, classical free electron theory, could not explain the photoelectric effect, Compton effect, and black body radiation. Now, according to this classical free electron theory, the value of specific heat of matter is given by 4.5 R, where R is the universal gas constant, whereas experimental value is nearly equal to 3 R. You know the generally the experimental value is going to be 3 R. Okay. Also, according to this theory, the value of electronic specific heat is equal to 3 by 2 R, while the actual value is about 0.01 R. Okay, this is the why uh, actual values are very less compared with the theoretical value. This classical electricity was not another thing. Though K by sigma T is constant, that is called as Riemann translation, which is a success of classical electron theory. But according to classical electron theory, but it is not a constant at low temperature. That means whenever if you are considering the from room temperature to the higher temperature, this K by sigma T is constant. But whenever if you go for low temperature, this K by sigma T is not constant. Not a constant. And also, ferromagnetism could not be explained by this theory. The theoretical value of paramagnetic susceptibility is greater than the experimental value. That means whenever if you are considering the paramagnetic theoretical value of paramagnetic susceptibility psi is greater than the experimental value. This is also not explained by classical free electron theory. Okay, now coming to the another is about the drawbacks which are present with the classical free electron theory. Now we can go for the just wait for a minute. Wait for a minute. The quantum free electron theory. Now this is about the next concept is quantum free electron theory. That means some drawbacks are present in the classical free electron theory. That drawbacks were successfully rectified by the quantum free electron theory. Why? Because this quantum free electron theory, which was proposed by Sommerfeld in 1928, retaining the concept of free electrons moving in a uniform potential within the metal as the classical theory, but treated the electrons as obeying the laws of quantum mechanics. That means Sommerfeld, Sommerfeld proposed this theory in 1928, retaining the concept of free electrons moving in a uniform potential, but this but Sommerfeld treated the electrons as obeying the laws of quantum mechanics. That means previously the classical free electron theory, uh, the electrons can be treated as normal classical electrons or which obeys the classical mechanics. But here we need to consider the quantum free electron theory or quantum mechanics. Based on the de Broglie wave concept, we assumed that the moving electron behaves as if it were a system of waves called matter waves. That means whenever if you are considering a wave, according to this de Broglie concept, he assumed that whenever the electron is moving, which is associated with a wave, that's why that wave or the called as matter wave concept. That means wave is associated when it is moving. Whenever if you are considering a moving particle, that moving particle is associated with a wave. That wave is called as a de Broglie wave or it is a matter wave. According to this quantum mechanics, the energy of an electron in metal is quantized. The electrons are filled in a given energy level according to Pauli's exclusion principle. That means, what is that Pauli's exclusion principle? That no two electrons will have the same set of four quantum numbers. There are four quantum numbers, that is principal quantum number, azimuthal quantum number, and Sommerfeld quantum number, and spin quantum number. We need to consider among that four quantum numbers, no two electrons will have the same set of four quantum numbers. At least the one should be variables. Okay, that is each energy state is filled with two electrons. That is, one is if and only if those two magnitude is same, but the direction is going to be different. That is, the spin of the electron is not same. Okay, each energy level can provide only two states, namely one with spin up, that is one with the another spin down, and hence only two electrons can be occupied in the given energy level. That means whenever we are considering the quantum free electron theory, according to this de Broglie's concept of the Pauli's exclusion principle, in a given energy level, there are two electrons need to be occupied, but those two electrons are having opposite spins, even though they are having the same magnitude. Okay. Now, coming to this, it is assumed that the valence electrons travel in a constant potential inside the metal, but they are prevented from escaping the crystal by very high potential barriers at the ends of the crystal. That means whenever we are considering the valence electrons that are traveled freely in a constant potential field in the inside the material, but they are prevented from escaping the crystal by very high potential barrier at the ends of the crystal. Okay, now in this theory, though the energy levels of the electrons are discrete, what is meant by a discrete means discrete energy levels are very close energy levels which are having the same set of quantum numbers. That is, the spacing between the consecutive energy levels is very less, and thus the distribution of energy levels seems to be continuous. That is, whenever we are considering the discrete, the distribution of energy levels seems to be continuous. Okay. Now, according to this quantum mechanics, a conduction electron in a metal experiences a constant potential and free to move inside the crystal, but will not move out because of infinite potentials exist at the surface. That means if we are considering a potential well in which there is a infinitely depth well, that means infinitely high of the barrier. That's why it is not possible to escape from this one. The conduction electrons in metal experiences a constant potential within this and free to move inside the crystal, but not come out because an infinite potential exists at the surface. This theory explains electrical conductivity and also the thermal conductivity, but failed to explain the difference between conductors, insulators, and semiconductors. That is, this theory explains this quantum free electron theory explains the conductivity of thermal and electrical conductivities, but fail to explain the classification. On what basis these materials are classified? This quantum free electron theory was not explained. It failed. It fails to positive Hall coefficient of metals and the low conductivities of divalent metal. It is also failed to explain the low conductivities of divalent metals than monovalent metals. And some of the another now coming to the relevant zone theory, or simply called as band theory. That means previously the quantum free electron theory was not explained the is unable to explain the classification of metals. This band theory explains successfully the band classification of the solids. This band theory developed by Bloch. Bloch developed this theory in which the electrons moves in a periodic potential due to positive ions in metals. These are positive ions. These are positive ions. In between that, there is a periodic potential. An electron moves through these ions, it experiences a varying potential. That means if electron comes near to the positive ion, it experiences a what about the potential, that is it's going to be zero potential. Whenever if it is coming in between, that means if it is exactly at the center of the two positive ions, it experiences a maximum potential. It experiences a, it explains the mechanism of conductivity and semiconductivity on the basis of energy bands and hence the bandwidth theory. That means this Bloch explained based upon his periodic potentials or what is mechanism of conductivity and semiconductivity on the basis of energy bands and hence band theory. It explains if an electron moves through these ions, it experiences varying potentials. Okay, that is, if you can see the figure, in this figure, yes, you can see this. It experiences a varying potential. That means if you are considering the positive ions, these are lattice ions. The lattice ions are represented as a positive case, which is just simply a location of an atom. The potential of an electron at the positive ion site is zero. That means if we are considering the potential at this positive ion site, it is going to be zero. Okay, and whenever if we are considering the in between that, the maximum is in between the ions. Potential is maximum in between the positive ions. Positive ions, the potential experiences by an electron varies periodically. That means whenever if the electron comes near to the positive ion, it experiences a minimum potential. But whenever if it is far away from the electron, it experiences a maximum potential. That means it is periodically varying. Suppose if the electron is moving like this manner, whenever if it is comes near to the positive ion, it experiences a minimum potential. Goes further, it experiences a maximum potential. That means it can be very linear in a periodic manner. That is with the same period as the lattice. That is the potential experienced by the electron varies periodically with the same period as the lattice. The potential is negative because of attractive force between the electron and the positive ion. So we need to consider the potential is negative because the attractive force between the electron and positive force between the electron and positive ions. Along x direction in the crystal, the potential function V of x has periodically is V of x is equals to V of x plus V. That means we need to consider a lattice distance, capital E. We need to consider a distance A, that A is the lattice distance. The energies of the electrons can be known by solving Schrodinger's wave equation in such a lattice. That is, whenever if we are considering this Bloch function, that is the potential can be varied periodically. That is V of x is equals to V of x plus A. The energy of the electrons can be known by solving Schrodinger's wave equation, whether it is time dependent or time independent. Bloch showed a type of solution whenever if you are considering the Schrodinger wave equation. That is, you are UK of x is equals to UK of x plus A in V. Whenever if you are considering the Bloch function, which will psi of, we need to consider the wave function, psi of x plus NA is equals to UK of x plus NA into e power of ik into x plus NA. This is the wave function whenever if you are considering this Bloch theorem. That is, this can be explained by the Bloch. Okay, now coming to the another okay, it is about the Schrodinger's wave equation. There is time independent of Schrodinger's wave equation. D square psi by dx square plus 8 pi square n by s square into minus v of x into psi. Now here this wave function based upon this Bloch equation of Bloch theorem. We can use this solution. The psi k of x is equals to uk of x into e power of ik of x. Okay, that is uk of x can be written as or psi k of x plus na, that is equals to uk of x plus na. We need to write this. Psi k of x plus na is equals to uk of x into e power of ik plus e power of ik n. It is equals to psi k of psi of x in the power of I k. That means whenever if we are considering the psi k of x plus n is equals to psi of x. This is about the Bloch's theorem. That is, Bloch's theorem explains the what about the potential can be varied from one side to the another side. That is, from one point to the another point. Here, the potential can be varied periodically if the electron is moving in the positive lattice ion sides, or if you are considering a network of lattice ions, in that, there is a periodic potential variation. That's why it experiences a potential by the electron in periodic manner. That's why a negative potential is present because of the attractive force between the electron and the positive ions. Now we need to consider the Schrodinger's wave equation to explain this theorem, the wave equation of the particle present, the particle experiences the particle experiences a periodic potential. We need to use Schrodinger's wave equation. For this Schrodinger wave equation, we can use the Bloch theorem. Why? Because this Bloch theorem explains the what is the wave function at positive ion site and at a period of regular period of A. This is the case. Now coming to the another concept, we need to uh, consider the chronic Penny model. This is a qualitative treatment only. Here, this chronic Penny model is simply a sinusoidal potential shown in this figure. That is, you can see this. There is a potential variation is like this. Here it is going to be zero potential, and it is going to be a maximum potential like this. This is a potential well, or we can represent it with a square well potentials. That is rectangular potential. Here, this is what about the positive ion side, the positive ion side which is presented here. And what about the case? Here, this is A. Whenever we are considering the distance A is the lattice. Now, sinusoidal potential shown in theory, it is not easy to solve Schrodinger's equation with these potentials. So, chronic and Penny approximate. Yeah. Okay, maybe another 5 to 10 minutes. We need to concentrate on this because it is a sinusoidal potential in which we need to consider a rectangular steps, Schrodinger's wave equation. After solving this, what about the within in this region? What is the way of electron experiences a potential? For this one, we need to consider. And in this region, what is the potential experienced by the electron outside this one? We need to consider three regions in which that means the electron is moving like this. We need to consider the Schrodinger's equation solutions are as well only cos k is equals to p sin alpha over pi plus cos alpha, where p is the scattering power, p is equals to 4 pi square ma by s square dv naught psi omega. This is the potential barrier and dv naught omega barrier strength, where alpha is the 2 pi by h into square root of 2 m. This cos k